Welcome to the third lecture of my class on global homotopy theory. Last time I introduced the notion of global equivalences for orthogonal spectra. So a morphism of orthogonal spectra is a global equivalence if it induces an isomorphism on the G equivariant stable homotopy groups in all integer degrees and for all compact Lie groups G. Using this notion, I had defined the global stable homotopy category. So this is the localization in the sense of one category theory of the category of orthogonal spectra at the class of global equivalences. Something I already mentioned and that I'll come back to later is that there is a model structure in the background, the global model structure, and this is extremely useful for actually working with the global stable homotopy category. After that, I've started discussing the natural operations that exist on the equivariant stable homotopy groups of orthogonal spectra, and I treated the restriction homomorphisms, which are contravariant in a continuous homomorphism of the compact Lie groups. And they sort of decompose into two classes. There's restrictions to subgroups, and there's inflation homomorphisms, which are restrictions along continuous epimorphisms. The restriction homomorphisms are roughly speaking half of the natural structure that the equivariant stable homotopy groups of a global object support, and the other half are given by transfer maps. The transfer maps are really a feature that already exists one compact Lie group at a time, and I will now briefly review the most important things about transfer maps in this context. So the next aim of today's class is the following. So I want to recall the transfer homomorphism TRHG, which will go from an H equivariant homotopy group to a G equivariant homotopy group. And what is the context here? For a closed subgroup H of a compact Lie group G and an orthogonal G spectrum X, so an object in this category that I've noted as P sub G. So in my class on equivariant stable homotopy theory last term, I discussed the transfers in complete detail in the context of finite groups. I gave the constructions in the context of the Webmuller isomorphism, and I derived various properties. So following my general principle, I will now give you the relevant definitions, and I will state the properties that we'll need later in a precise form with references, but I will not give proofs for most of these properties. So there's a new feature coming up in the context of compact Lie groups as opposed to finite groups, and this is the tangent representation, so let me introduce it. So again, we have a closed subgroup of a compact Lie group G. This will in fact be the context for most of what I do today, so sometimes I will not write this down anymore, that H is a closed subgroup of G. So the tangent representation is the following. I will write L for it, and it's this tangent space at the preferred coset EH in the homogeneous space G mod H. Tangent space at H. This is the coset H itself in the homogeneous space G mod H. So let me make a bunch of comments about this definition. So the first comment is that in the context of finite groups, so when G and hence also H are finite, or slightly more generally, when H has finite index in G, then G mod H is just a finite discrete space, a zero-dimensional manifold, and then of course all the tangent spaces are trivial vector spaces, zero-dimensional vector spaces, and in that context not much is happening and there's no need to talk about it in the first place. So this is why you don't hear about this tangent representation in the context of finite groups only, so it's truly a phenomenon that comes up for positive dimensional compact Lie groups. So then, why did I call it an error representation? So at this point, it's only a vector space, and this is as follows. So G acts on G mod H by left translation. And G mod H is naturally a smooth closed manifold. You know, these are all compact Lie groups. And then the left translation action is, of course, smooth, and so the subgroup also acts. And so does H. This special coset, EH, H itself, is invariant under left translation by H. So it's a fixed point of this action. So because EH is fixed by H, by the left translation action, we can differentiate the action and we get a linear action on the tangent space at this fixed point. The differential of the translation action is a linear H action on this tangent space. So far I had restricted the term representation to an action of a compact Lie group that leaves some inner product invariant. So on the face of it, this L doesn't come with an inner product. Sometimes I will nevertheless use one, and that I can do because if a compact Lie group acts on a finite dimensional vector space, there always exists an invariant inner product. Basically, you just choose an arbitrary inner product and then you average over the action using the Haar measure of the compact Lie group G. Associated to the closed subgroup H of the compact Lie group G is this tangent H representation, and what is its dimension? Well, the dimension of the tangent space is, of course, the dimension of the manifold, in this case the homogeneous space G mod H, and this is just the difference of the dimensions. The ambient group G and its subgroup H. So the H action on this tangent representation L may or may not be trivial, and this can make a difference for various things. So let me point out one situation in which it's always trivial. So if H is normal in G, then H acts trivially on G mod H altogether. And if it acts trivially on the whole manifold, it also acts trivially on the tangent bundle, it acts trivially everywhere, and hence also on L. So this includes in particular the case where the ambient group G is an abelian compact Lie group. So for abelian compact Lie groups, this tangent representation is always untwisted. It always has a trivial action. Slightly more generally, it would be enough that the normalizer of H in G has finite index in G, and then we would also get that this is the trivial action. So if you haven't come across these tangent representations before, then I think it's a good idea to familiarize yourself with it a little bit. And to this end, I'm suggesting two exercises that you can do, which will you see in these overlay slides now. The first exercise is a very concrete one. So there we let the ambient group G be the second orthogonal group, and we consider two different conjugacy classes of finite subgroups with two elements. So on the one hand side, we can consider minus the identity, so that's the central element that's given by the diagonal matrix -1, -1. This generates a subgroup of order 2 in the orthogonal group. And we can also look at the subgroup with two elements generated by any of the reflections. All the reflections are conjugate, so it doesn't really matter which one you choose. These are two subgroups that are not conjugate with two elements in O2. So in this situation, the tangent representation will be one-dimensional. And for a group with two elements to act on a one-dimensional vector space, there are basically two possibilities. It could act trivially, or it could act via the sign. And the exercise for you is to figure out in which of these two cases the two conjugacy classes fall. So when you get the trivial tangent representation and when you get the sign tangent representation. The other exercise is more of a general structural kind. So it's about different conditions on the ambient group, compact Lie group G. The exercise is to show that the following conditions are equivalent. The first one says that the identity path component of the group G is central in the group G. This condition is equivalent to the property that the group is isomorphic to a product of a finite group and a torus, where a torus is a connected compact abelian compact Lie group. And these are classified, these are always finite products of circle groups, finite copies of the group U1. The third condition, which is equivalent to the first two, is that for every closed subgroup H of G, the tangent H representation is trivial. So this gives a characterization of those ambient groups G such that no matter which subgroup H you take, the tangent representation is trivial. So now, after you've done these exercises, I can come back to the construction, and now I'll do something that's a little bit more general than the transfer that we're mainly after. So this is a construction of the so-called dimension shifting transfer. So this is a transfer that I'll denote by a capital T, R, HG, and it goes from the kth H equivariant homotopy group of X smash the one-point compactification of the tangent representation L to the kth G equivariant homotopy group of X, where again X is an orthogonal G spectrum. So the terminology, dimension shifting transfer, is not completely uniform, but I like this terminology because it basically a transfer that shifts the dimension. So let me try to explain this. So if H happens to act trivially on L, and I've just told you a bunch of situations where this is the case, so then the kth H equivariant homotopy group of X smash SL, now this is a trivial action, so by the suspension isomorphism, this is isomorphic to the K minus the dimension of L, H equivariant homotopy group of X. So if the action happens to be trivial, then this transfer is really shifting the dimension exactly by the dimension of the tangent representation, or equivalently by the difference of the dimensions of G and H. But if the action is non-trivial, then you should think of this as some kind of twisted version of shifting the dimension. It's sort of shifting the dimension in the ROG graded sense, just that I'm not really talking about ROG graded homotopy groups here. So in the previous class, in the context of finite groups and also in my book on global homotopy theory, I deduced this transfer as a consequence of the Wittmüller isomorphism. The Wittmüller isomorphism is a very important result in equivariant stable homotopy theory. Still, for the purposes of this class, I want to take a more geodesic route and define this dimension shifting transfer more directly. If you want to see the other approach, you can look it up in the book. So the construction of this dimension shifting transfer depends on a choice. So we have to choose a G representation V and a vector little v in V with isotropy group H. So this vector is fixed by H, and no group element outside of H fixes this vector. So why does such a pair exist? Well, in this special case, when A happens to have a finite index in G, then G mod H is a finite G set, and you could just take the permutation representation, and that will do the job. In general, you have to quote the Peter-Weyl theorem again, and it will provide in particular the existence of such a representation and such a vector. So, because the isotropy group is exactly H, we can look at this map from G mod H to V that sends a coset little gh to G times V, and because the stabilizer of the vector V is exactly H, this is an embedding. There's a smooth embedding, it's injective. So in particular, we can take the differential of this smooth embedding at the preferred coset. So the differential of I at the preferred coset EH This starts from L, the tangent space at EH in G mod H. And this is going to be a linear isomorphism onto the tangent space of the target, which is based at the vector V, and it's the orbit GV, because the image of this embedding is exactly the orbit of the vector. So this is an H-equivariant linear isomorphism. So this gives us another sort of interpretation of the tangent representation. If we've chosen this V and this little v, then we can see it as the tangent to the orbit GV at the vector little v. So now we'll define W as the orthogonal complement. So V has an inner product. This minus sign is not the set theoretic complement, it's the orthogonal complement of the orbit in here. And this is again an H representation. Because this was H invariant, its orthogonal complement is also H invariant, but it's typically not a G invariant subspace. So let me now write D of W for the unit disk. So all vectors X and W that have length at most 1. So after possibly scaling the vector V by a sufficiently large real number, we can assume that the exponential map so what is this? So this is a map from G amalgamated with the disk of W to V. And this is the map that sends the equivalence class of a pair G comma W to G times V plus W, so that this is injective. So you know, if the vector lies too close to the origin, then if you're less than your length 1 away on different points of the orbit, you might get the same point. So to avoid that, we multiply little v with some large enough number, and then we can arrange this injectivity property. And actually, it's enough, in particular, if I want to treat a particular example later, to have this injective on the open unit disk. So where the vectors have length strictly less than 1. So the image is then the tubular neighborhood of the orbit. Image of this map, which I want to call little j, with tubular neighborhood of the orbit GV inside V, and by definition it's a G invariant tubular neighborhood. Such invariant tubular neighborhoods are always guaranteed to exist for smooth equivariant submanifolds by general principles, but here we can get one very explicitly. You know, on the open unit disk we have an open embedding, and such an open embedding then has a map in the other direction that's called the collapse map. So this is a map in the other direction. So it goes from the one-point compactification here, and it would go to the one-point compactification of the extension of the open unit disk, but I will scale this by a suitable scaling function to make it land in this construction, G semidirect L S W. So this symbol, which is also the symbol for a semidirect product of groups, but I use it as an abbreviation for the based version of inducing up an action. So this is my notation for G with a disjoint base point smashed with SW, and then you co-equalize the two H actions, one by right translation on G and then the given H action on W. So this collapse map sends a point of the form in the image of the point G times V plus W with length of W strictly less than 1 to the point G smash, and then I use W divided over 1 minus the length of W and it sends the complement, now this is the set theoretic complement of the open tubular neighborhoods, so this would be J of G times over H with the open unit disk to the base point. So the particular function that I use here for scaling is not so important. What is important is that this function, sending a vector, dividing a vector by 1 minus its length, is a function that scales the unit disk all the way out to minus infinity plus infinity. You could basically use any other function that serves the same purpose, some diffeomorphism from the open interval minus 1, 1 to the real numbers in the same way. I just use a specific one, and you probably want to use the same function all the time you're dealing with this. So there's a different way to say this. Is the collapse map is basically the inverse of the open embedding on the open unit disk wherever that is defined. Well, it's not quite the inverse because I'm also using this scaling factor, and the rest, the complement of the image, goes to the point at infinity. So now I can define the dimension shifting transfer, but I need some more space, so I have to erase the blackboard again. Now I use the collapse map that we've just constructed, and which is G equivariant, to define the dimension shifting transfer, which goes from the zeroth H equivariant homotopy group of X smash the sphere of the tangent representation to the G equivariant homotopy group of X in dimension 0. So I restrict to dimension 0 here just to simplify the notation. The general construction is exactly the same, just with an extra r to the k or with an extra shift in the x variable. So an element on the left-hand side is represented by a map of this kind, so that f from S u to x of u smash SL represent a class in the group pi 0 h of x smash SL. So it is an H equivariant based continuous map, and u a priori is an H representation. But now, without loss of generality, I can and I will assume that U is underlying a G representation. So it is of course not true that an H representation is always underlying a G representation. Some H actions simply don't extend. However, I can always embed every given H representation into a representation that's restricted from G. That's again a consequence of the Peter-Weyl theorem. So that means I might have to change the representative for this class by stabilizing it with some other H representation. But after stabilizing the representative, if necessary, afterwards I can assume that U is coming from a G representation, and I will assume this now. So now I'm going to do something else to this representative. I'm going to stabilize it from the right-hand side by the H representation W. So we stabilize F by W. So this gives us the following. I go from U direct sum W via the map F smash the identity on the W sphere to X of U smash SL direct sum W. This I can identify with X of U smash SV. So why can I do this? Well, remember that the differential of the embedding I was an identification of L with the tangent space at V of the orbit, and W was exactly the orthogonal complement. So this identification is given by the differential of the embedding I on L and just by the inclusion of W. And this is all an H equivariant identification. And now I can use the opposite structure map, sigma U V op, to go to X of U direct sum V. This composite is what I've earlier denoted by the stabilization of X from the right with W. Well, not quite, because we're also using this identification here, but except for that, that's what it is. So this is still an H equivariant map, and now we can use this to define a representative for the transfer. So now we can do the following. The composite. So this map up there is H equivariant, but now we'll have a composite of G equivariant maps. So I start from U direct sum V. Now I'm going to exploit that U was assumed to underlie a G representation, so this is now a G space. I use the identity on the sphere of U, smash the collapse map that we've previously constructed. This goes to SU smash G over H from SW. Run this way. So then I use a shearing isomorphism that I'll explain in a second to get me to G extended from H with SU smash SW. So to have this shearing isomorphism, I also use the G action on U that I had assumed without loss of generality. Now I'm going to use the adjoint of the H equivariant map that was the stabilization of G. And this gets me to X of U direct sum V. So this is the adjoint of F diamond W. So this was only H equivariant. But the target comes to us with a G action because V was a G representation and U we'd assumed to be a G representation. And this functor is the based version of extension of scalars from H to G. So an H equivariant map from here gives by adjoint as a G equivariant map from here. I still have to explain this shearing isomorphism. So the shearing isomorphism sends a U smash the equivalence class of a GA to the class of G and then G inverse U smash A. And it's a G equivariant isomorphism, and it also exploits that we have a G action on U. So this composite is a G equivariant map, and this represents the transfer. So this represents the class that I wrote capital transfer R, the dimension shifting transfer, applied to the original class F, and it lives exactly where it's supposed to live, because the G representation here is the same as the G representation here. It's a G equivariant based map. So again, I have to use the more general construction, how to represent elements in equivariant homotopy groups, where the representation don't necessarily have to be sub-representations of the chosen complete universe. What's relevant is that you have the same representation here and here, which we have. So it's perfectly fine. It represents an element in the equivariant homotopy group of G. So of course there are now various things to check, and I will not do these checks here. I will just tell you some of the things that you would have to check. You can read it up, for example, in the book on global homotopy theory. So of course you have to check well-definedness, and this involves several things. We've made several choices, and you have to check that the resulting class doesn't depend on this. So what were the choices? Well, the choice of representation capital V and vector little v with isotropy group H. This was one of the choices. Then we started with a representative. We allowed ourselves to stabilize the representative so that U is underlying a G representation. This is a choice. And of course, if you have all the other choices fixed and you vary the original F by an equivariant, H equivariant homotopy, then this result will vary by a G equivariant homotopy. So this is the easy part of the verifications. So taking this for granted that everything is well defined, then this construction is clearly natural in the orthogonal spectrum X for homomorphisms of orthogonal G spectra. Another thing you would have to check, which is not completely obvious from the way I've presented it here, is that this transfer map is actually a homomorphism of abelian groups. This is not completely obvious. If you think of the group structure as coming from pinching in some H fixed sphere, there are other ways of setting it up so that you don't have to explicitly work with pinch constructions. The definition of the dimension shifting transfer was fairly general and fairly abstract, and it could be a little overwhelming if you see it for the first time. So I would like to go through an example. The main geometric ingredient for the dimension shifting transfer was this collapse map, and that's really the thing that I would like to review in what I think of as the simplest non-trivial example. So simple is relative to the fact that I've discussed all of these things in the context of finite groups last term. So I want to take the simplest non-trivial example where you actually have Lie groups of positive dimensions. So the example that I want to discuss is where the big group is the circle group U of 1, or if you prefer, SO2, and where H is the trivial subgroup. So just to briefly remind you, if the group G and hence also H is finite, or more generally, if G mod H is a finite set, so when you have H has finite index in G, then you're basically embedding a bunch of points on which G acts into a representation, and then the collapse map is just a collapse map around little balls, disjoint little balls around these finitely many points, and these balls are permuted by the G action around. So if the dimension between H and G is different, if the dimension goes up, then a little bit more is happening. Some of this is illustrated by this example. The example does not show the full complexity of the situation because some things are special. You know, for example, the group I'm considering is abelian and the subgroup I'm considering is trivial, so necessarily every H representation is trivial here. So I'm not sort of showing the full complexity of the situation, but nevertheless I think this illustrates some of the features that go into this. So in this situation, I would be discussing the dimension shifting transfer from the trivial group to U1, which would go from pi 0 relative equivariant for the trivial group from X smash the tangent representation. Well, since the group is trivial, the representation necessarily has to be trivial, so it's one-dimensional. So if we make some choice of identification of the tangent space with the real numbers, we can identify this with X smash S1. So let me do dimension 1 here. And this would go to pi U1 equivariant in dimension 1 of X. And this, via the suspension isomorphism, we can identify with pi 0 non-equivariant of X. And so this is an example where the dimension shifting transfer is really shifting the dimension because there's no twist in the representation. Okay, so now let's go through the construction. So the first thing we have to choose is this representation V and the vector little v. So we need some G representation, so some U1 representation, which has a vector that has trivial isotropy groups, so a free vector. And the simplest thing that I can think of is we take V to be the complex numbers with this tautological U1 action. So U1 is the group of complex numbers of length 1, and it acts by scalar multiplication, tautological U1 action. And this representation, like in any representation, the origin is fixed, but any other vector is a free vector, so we could choose whichever vector we wanted. So let me just choose the most obvious one. Let me choose the 1 in the complex numbers, and then I'll draw some pictures. So if we make these choices, what is the embedding I going to be? So in general, it would start from U mod H, from G mod H. So H is the trivial group, so it will just be a G equivariant map from the group G, which is U1. And it will go into the complex numbers, and we basically react with some complex number of length 1 on the chosen vector, which is 1. So this is simply the embedding, the inclusion. Maybe I should have said this at the beginning, but this for me is just the complex numbers of length 1 with the group structure by multiplication. So here's a picture. So here I draw the complex numbers. So this is the real direction, this is the imaginary direction, here's the origin, here's 1. This is our preferred vector, I minus 1. Then I'll draw the image of this embedding, so that's just U1 itself. Okay, so I guess this is slightly distorted circle, it's supposed to be the unit circle. So then we'll have this tubular neighborhood, and this will be the image of all the points that are at length strictly less than 1 away from this orbit. So let me draw this. So if this is 2, it will be the unit disk of length 2 around this. So that's the tubular neighborhood without the point 0 and not with the stuff outside there. And I can now draw also the tangent representation and the normal representation. So we're looking at this vector, this is the orbit. So the tangent space is this. So what would be our L, or what's isomorphic to L, is the tangent space at 1 of U1. And this we can identify with the imaginary axis. And then the W was the thing that's orthogonal to this. So that's this direction. The W in this situation is the real numbers as opposed to the imaginary numbers. Okay, so now what does the collapse map do? Well, the points in here, so we're not looking at the origin and not the stuff that has length 2 or larger. So if there's some vector on the unit circle, then you look at this line segment, which is length 2, and you basically scale it. You move this point to the origin, and you scale the rest so that -1 + 1, this distance goes out to infinity. And you could work out the formula in this particular example. It's not a nice formula, so I will do something slightly different. So I will give a homotopic, I will give a formula for a homotopic map. And for that you can imagine that instead of scaling -1 + 1 all the way to -infinity, 0, infinity, I'm just going to scale everything from here, 0 to +infinity, to -infinity, +infinity, and one function that does the job is the logarithm function. So here's a U1 map, which is equivariantly homotopic to the one I've previously defined. Equivariantly homotopic to the collapse map. So the collapse map would go from the one-point compactification of the complex numbers with a U1 action by scalar multiplication. And it would go, well, in this particular case, it goes to S1 / U1 plus. So in general, I would have to induce up from the trivial group. There is no trivial group, so I'm not recording it here. And also the action on S1 is trivial. You know, after all, this is an abelian compact Lie group, and also the subgroup is trivial. So this is two reasons for why the action, this would be the W in general with trivial action in this particular example. And so here's a formula that you can use. You can send this to the logarithm of the length of lambda times smashed with the normalization of lambda, and this is for lambda not 0, and to the point at infinity, or the base point, if lambda is 0. So as I said, this is not the formula for the one that I've given in general on the last slide, but it's kind of a slightly different scaling function, which nevertheless is homotopic to the previous one. So this is a specific example of what the collapse map can look like. And then the second step, how you get from the collapse map to the external transfer, this was just some playing around with the junctions and shearing isomorphisms. From the dimension shifting transfer that I've discussed on the previous whiteboards, I can now define the degree 0 transfer that we're mostly interested in. So if I need to emphasize this, I call it the degree 0 transfer, but most of the time I'll just say the transfer for this one, which doesn't shift dimension. So this is with a little t. It goes from the H equivariant homotopy group in dimension k of x to the G equivariant homotopy group in the same dimensions, so no shift in dimensions, is the composite of the transfer that possibly shifts the dimension with the homomorphism that's induced by something that I'll call x smash a lower star, which goes from pi 0 k h equivariant of x to pi k h equivariant of x smash SL, and then on with the other transfer where A is the map from S0 to SL that just includes the point at the origin and the base point at infinity. This is the inclusion of 0 and infinity. Remember that infinity is always the base point. G is another fixed point that you have in every representation of a compact Lie group. It might or might not be the only other fixed point. So, as I said, the only difference is you first do this inclusion of the fixed points, and then you do the dimension shifting transfer, and then this composite is denoted little trh of G. So, this map is induced by a morphism of orthogonal G spectra, so it's clearly natural in X, and it is a homomorphism of abelian groups, and the big transfer is a homomorphism of abelian groups. So we directly conclude that the little transfer is also natural and a homomorphism. So there's a natural for morphisms of orthogonal G spectra in X, homomorphism of abelian groups. Now I would like, for the first time, to actually prove something in this lecture. So far I've given you lots of definitions and some constructions and references, but I haven't yet proved anything, so that's what I want to do now. So this proof will not be terribly difficult or deep, so I'll just call it a lemma, but nevertheless it requires an argument. So here's following: let H be a closed subgroup of a compactly grouped G. And then if H has infinite index in its normalizer, the normalizer in G, then the degree 0 transfer is the trivial homomorphism. It's the 0 homomorphism for all x, all orthogonal G spectra x. So it's the 0 natural transformation. Before I start the proof, one or two comments. So the first comment is that in the context of compact Lie groups, where we're always working, saying that H has infinite index in its normalizer is equivalent to saying that the normalizer has a strictly larger dimension. And another comment that I want to make is that while the degree 0 transfer in this situation is the 0 homomorphism, the dimension shifting transfer is generically non-zero. So in other words, there exists an orthogonal G spectrum X for which the dimension shifting transfer is non-zero, or the dimension shifting transfer as a natural transformation is always non-zero, even if H has infinite index in its normalizer. So that's a key difference between the dimension shifting and the degree 0 transfer. Of course, I mean, it's kind of possible that you lose information by precomposing with this, and as the proof will show, in this situation you are actually losing a lot of information. So here's the argument. So the inclusion of the normalizer into G is, of course, H equivariant for the right translation action, so it induces a smooth embedding. A smooth embedding just induced by the inclusion of the normalizer into the big group is H equivariant for the translation action. The distinguished coset is an H fixed points of the source and the target, and it induces an H equivariant linear monomorphism on the tangent spaces, from the tangent space of the preferred coset in NGH mod H to the tangent space of the preferred coset in G mod H, which by definition was RL. So now, by design, H is normal in its normalizer, and that's what the normalizer is made for. H is normal in NGH, it's the largest subgroup in which H is normal. So that means that on this orbit space, the H action is trivial. The translation action is trivial. On NGH mod H, and hence also on the tangent space. That's the H in normalizer GH mod H. On the other hand, we assumed in the hypothesis that H has infinite index in its normalizer, or equivalently, the normalizer has strictly larger dimension than H. So that means that the dimension, so because H has infinite index in its normalizer, the dimension of this tangent space, TEH in normalizer GH mod H, which is of course the dimension difference. So this is the difference of the dimensions of NGH and H. This is a positive number. So that means we have an H representation with trivial action embedded here, this one, embedded H equivariantly into the other H representation where we don't know much about it, but we conclude definitely that the H fixed subspace has positive dimension. So if I take LH, the H invariant vectors in L, which is a linear subspace, has positive dimension. So, as I said earlier, in the one-point compactification of L, we have always two fixed points, the point 0 and the point infinity, and in general this might be the only fixed points. But if the fixed points of H have positive dimension, then there's at least one line joining 0 to infinity in the one-point compactification. So that means that the inclusion from S0 into SL is H equivariantly null homotopic. We just choose some non-zero vector in L that's fixed by H, and then you choose the ray that's spanned by this vector to homotope the point 0 to the base point at infinity. And that's the end of the proof, because if this map is H equivariantly null homotopic, then smashing it with some orthogonal spectrum is going to be an H equivariantly null homotopic map. And of course then the first composite that is half of the definition of the degree 0 transfer is the 0 map. So this means X smash A lower star is the 0 homomorphism, and then of course the composite is also the 0 homomorphism. And that's the end of the proof. Next, I would like to discuss some of the properties of the transfers that we will need later. Again, I have proved all these properties in the context of finite groups last term, so now I will basically just state them without proofs, but I will overlay some references in the video. The transfers that I will now talk about will usually be the degree 0 transfers, but most of the properties, except for the double coset formula, most of the properties that I will now write down have precursors for the dimension shifting transfers, and you can find those, for example, in the Global Homotopy Theory book. And while I write things about transfers, X will always refer to an orthogonal G spectrum, where G will be the ambient group in which everything happens. So the first property is that transfers are transitive. And this is very easy to state for the degree 0 transfer. So let K inside H inside G be a triple of nested closed subgroups. And the most obvious relation actually holds. So you can take the two individual transfers. You can go from pi k equivariant of x with a transfer to h to pi k h equivariant of x. And then you can go to pi k g equivariant of x via the second transfer from h to g. And this composite coincides the transfer in one go from K to G. In the precursor of this, for the dimension shifting transfer, you also have to make some identifications of tangents representations, but it's not very much more complicated. The next property is that transfers commute with inflations. So this is a slogan that's slightly imprecise, but I'm giving you the precise statement right now. So we have, again, a closed subgroup. Let H inside G be a closed subgroup. And then I'm looking at inflation, so that means I have a continuous epimorphism, alpha from K to G. Continuous epimorphism. So then we can take the subgroup H in G and look at its pre-image under alpha. I call this L. Let L equal alpha inverse of H be the pre-image. This is a closed subgroup of K. The notation is a little bit unfortunate because until a while ago L always denoted the tangent representation of H in G, but I'm so used to calling the subgroup L that I sort of can't switch, so L right now has this meaning. And in this situation, the precise formulation of the slogan that transfers commute with inflation is the following commutative square. So what can we do in this situation? We can start from the H equivariant homotopy group. Let me just write it down for degree 0. It's the same in all integer degrees. We can transfer from H to G, pi 0 G equivariant of X. And then we can use the inflation homomorphism, a restriction along this continuous epimorphism, and this lands us in pi 0 K equivariant. And then in this generality, we would have the orthogonal K spectrum alpha upper star of X. Or we can do it in the other order. We can also inflate, because we can first restrict alpha to L, and then by design, L was the inverse image of H. This is going to be a continuous epimorphism from L to H. So we can use the restriction or inflation along this homomorphism. This gets us to pi 0 L equivariant of X, and that's a closed subgroup of K, so we then can transfer from L to K, and this is the precise way in which transfer commutes with inflation. As I already emphasized in the last lecture, a general restriction homomorphism is always a composite, because a homomorphism is first an epimorphism onto its image and then the inclusion of the image. A general restriction homomorphism is you first restrict to a subgroup and then you inflate. And the behavior of transfers with inflations follows a very simple rule. Transfers also interact with restrictions in a way that is well understood, but the precise relationship is more complicated. It's called the double coset formula, and I will explain things about the double coset formula on the next whiteboard. For the double coset formula, we have two closed subgroups of a compactly group G. But other than that, they're both sitting inside G. They don't have to have anything to do with each other. They're not sitting inside of each other or anything like that. And the double coset formula is a way to express the transfer from H to G, followed by the restriction from G to K, as a sum of terms that are basically transfers and restrictions in the other order, where you first do a restriction and then some kind of conjugation map and then a transfer. The double coset formula is important because it basically allows you to re-express composites of transfers restrictions in a kind of normal form, where you always do the restrictions first, then the conjugations, and then the transfers. So before giving you the general double coset formula, I would like to remind you of a special case that we discussed last term, namely that's when G and hence H are finite, or more generally when H has finite index in G. Suppose that the index of H in G is finite. And then the double coset formula is the following relation. It's a sum over double cosets, K, G, H, in the set of double cosets. Now if H has finite index in G, then already G modulo H is a finite set, with a discrete topology if you want, and then you divide out by the left K action also, so it's typically an even smaller finite set, but it's nevertheless still a finite set, so the sum is going to be over elements of this finite set, and it's going to be the following expression. So first you restrict from the subgroup H to the intersection of K conjugated by G with H. So let me remind you that K upper G is the conjugate subgroup, K inverse times K times G. If I write the G on the other side, you'll have the G on the left and the G inverse on the right. So then this is followed by a conjugation map, G lower star, that I'll tell you about in a second. And then we transfer from K intersected GH all the way up to K. So that's the formula. So I have to explain you what this conjugation homomorphism is. And it's the following composite. So we can start from, well, let me do this maybe just on zero equivariant homotopy groups. So this is a relation as maps from pi 0h equivariant of x to pi 0k equivariant of x, where x as usual is an orthogonal G spectrum. So this map G lower star then has to be a map from pi 0, and the group of equivariants is k conjugated by G and intersected with h of x. And we first do the conjugation homomorphism. CG upper star, remember, was the homomorphism that conjugates by G. So this will land us in pi 0, and now we have the conjugation on the other side. And inside we have CG upper star of x, the orthogonal G spectrum, where the action of G is twisted by the inner automorphism, and then we restrict down to k intersected the left conjugate of h. And then we do the effect of LG lower star. LG was left multiplication by G, which is a G equivariant homomorphism from this G spectrum back to G, and we look at its effect on equivariant homotopy groups for this group of equivariants, K0, GH of X, and this composite I call G lower star. This is kind of conjugation homomorphism. I would like to remind you at this point that if the element little g happens to be in this group, then we had a proposition a little bit earlier which says that this composite is the identity, that this is inverse to this. So if G happens to belong to this group, this is the identity. But in general, of course, it will be some homomorphism that we don't really know very much about, and it comes up in this formula. So the sum is really taken over elements in this double coset set, so over you pick representatives, and it's a fun exercise to convince yourself that this term on the right-hand side really only depends on the double coset KGH and not on the representative G that we've chosen inside. So this is the double coset formula for finite groups that I've proved last term, and the proof pretty much works in the same way when H is finite index in G. The general double coset formula in the realm of compact Lie groups that we need is quite a bit more complicated. And the issue can be traced back to the fact that this double cosets, G divided out by the left K action and the right H action, in the general context will not be a discrete set anymore, it will not be finite anymore. Well, we want to give this the quotient topology by this action of K and G. And then it's not even a particularly nice space in general anymore. So the homogeneous space G mod H is always naturally a compact, smooth, closed manifold, and the translation action of G on it is smooth. But when you then divide out the K action from the left, there might be all sorts of singularities showing up, and this is a topological space, it's a compact topological space. But in general, it will not even be a topological manifold, and even if it is, it's not so clear what kind of smooth structure this would have if it does, and it's not. So it is not a reasonable thing to try to index by points in the double coset space anymore, because this will be infinitely many. And it's not so clear a priori what exactly we will put in place of this summation here. And as I'll start explaining on the next blackboard, what saves that is that this double coset space, while it's not a smooth manifold in itself, it naturally comes with a stratification by locally closed subsets, and each of these locally closed subsets is actually a smooth manifold in a very natural way, typically not compact. And what we're going to index over, what replaces the elements in the double coset set here, will be the path components of these locally closed subspaces, which are manifolds. In full generality, the double coset formula is more involved. I will now write down the statement first, then there'll be various unexplained terms, and then I will slowly go through the individual terms that show up and try to explain as well as I can. So we're in the context of a compact Lie group G and two closed subgroups K and H. And then, as before, the double coset formula is an expression for this composite. You first transfer from H to G, and then you restrict from G to H. So again, this will be a sum of terms And I'll explain in a second what the sum will be indexed over. Let me just write M right now. So this M will be connected smooth manifolds, typically non-compact, that have to do with a double coset space. And then there will be a summing that looks very similar to what we had before. The restriction from H to K conjugated by G with H. Then the conjugation homomorphism G lower star. Then the transfer from K intersected GH up to K. So this is exactly the same term that we had in the previous double coset formula. But now there's an additional coefficient, namely the internal Euler characteristic, that's what it's called, of M. So this is some integer, could be positive, negative, and it could be 0. So that's the general form of the double coset formula, and now there's various things for me to explain. So first of all, what exactly are we summing over? So, and this is kind of a nested summation. So the outer summation is over conjugacy classes of subgroups of K. Conjugacy classes round brackets L of closed subgroups of K. So for each such conjugacy class, we can look at a certain K-invariant subset of the homogeneous space G mod H, and I call this G mod H sub round brackets L. Round brackets L is the conjugacy class, so these are all cosets GH in G mod H, with the property that the stabilizer in K of GH is in the conjugacy class of L. So G mod H has a K action by left translation. So I can look at the stabilizer of this element inside of the group K, and I collect all of those together for which these stabilizers are in this conjugacy class of L. By not insisting that the stabilizer is equal to L, but conjugate to L, this becomes a K-invariant subset. It's again a locally closed inside the whole space, and this is naturally a smooth manifold, but typically non-compact. So as I said, it's K-invariant, so K acts on this, and because this has only one single conjugacy class of isotropy, the quotient map is again nice, and if we divide out the action of K on the left, on this again is naturally a smooth manifold. Actually, the quotient map is a smooth fiber bundle. But typically not compact. So we're summing over conjugacy classes of subgroups of K, closed subgroups of K, and there will be typically infinitely many such conjugacy classes. Nevertheless, this sum will only be finite because one fact is that this will almost always be 0. So this orbit type manifold, as it's called, G mod HL, is empty for almost all conjugacy classes. So there's a more general fact behind this. If a compact Lie group, in this case K, acts smoothly on a closed smooth manifold, then you can define the same kind of orbit type manifolds, and almost all of them will be empty. There will only be finitely many conjugacy classes of isotropy groups shown up. Okay, so because this is a smooth manifold, not necessarily, well, typically not compact, it will have connected components, and that's what the inner sum is over. So the outer sum is over conjugacy classes of subgroups, only finitely many will actually contribute, and this is then over conjugacy, over connected components M of this manifold K divided out on G mod H. L. So it's really a double sum over L and over M, but I guess I've sort of made this clear right now. What are the other ingredients? So the next thing is this G. This G is really something that depends on M, although this is not apparent from the notation. So the G in G is such that the double coset KGH belongs to M. So once you run over all L's and then over connected components M of this, then in it you choose some KGH, and again it's a fun exercise to check that the summand, this composite operation here, really only depends on the connected component M and not on the representative G that you choose for the double coset that lies inside of this. Okay, so now I've explained what the sum's running over, what the G has to do with the M. This is the same term as in the previous double coset formula, so I think all of the terms are defined. So the only thing left is to define this. So this, as I said, is an integer. So this chi sharp of M is an Euler characteristic. It's called the internal Euler characteristic. Of M, and one way to define it is as the Euler characteristic of M bar minus the Euler characteristic of the boundary of M. What are these? So M bar is the closure of M inside K mod G mod H. So while this is not a manifold anymore, it's a topological space, or the quotient topology, so you can take a closure in the point set topology sense, and then boundary M is thus the complement M bar minus M. So now the set theoretic complement. Okay, so I should warn you that while the notation looks a little bit like this M bar will in general not even be a topological manifold with boundary. This is really the closure in the sense of point set topology, and boundary M will not be the boundary in the sense of a manifold. So there's actually a little bit of subtle arguments involved here that this internal Euler characteristic even makes sense. So, we want this to be an integer, and we want this to be an integer too. And of course, for an arbitrary topological space, if we took the Euler characteristic based on singular homology or cohomology, there would be no reason for this cohomology theory to be finitely generated in finitely many degrees. So there's actually some arguments involved in showing that this Euler characteristic is a well-defined integer, and each of these individually are well-defined integers. Now everything's defined, the formula makes sense. I've told you what the sum is actually over. The sum turns out to be a finite sum because two non-obvious facts sort of happen here, that there's only contributions from finitely many conjugacy classes, and then this manifold, while it's not compact, only has finitely many path components. There's another new feature that I want to alert to. While this is always a correct formula in the context of compact Lie groups, in this more general context that we're in right now, it's perfectly possible that this group, K intersected the G conjugate of H, might have infinite index in K, or it might have smaller dimension than K. This is now perfectly possible, and it can come up, and it will come up. So that means that while the formula is correct, this transfer might, by the thing that we've discussed previously, might just be zero. So while there might be a certain number of summands, it's possible that not all of them contribute, for the reason that this transfer is one of these transfers that generically vanishes. So that's perfectly possible. And then the very last comment is that how does this specialize to the previous and easier double coset formula? Well, in the situation where H has finite index in G, then the double coset space is just a discrete space with finitely many points, and then of course all these manifolds here are just zero-dimensional manifolds. Their connected components are all just points, and then the internal Euler characteristic is always 1 because the closure of the point is the point itself and you're not subtracting anything. So in the case where H has finite index in G, we're really summing over the points in the double coset set. So over the double cosets themselves, this coefficient is always 1, and that's how we reduce to the simpler double coset formula in that case. A brief comment on the history of this general double coset formula. So this formula was first proved by Mark Feschbach in a special case, namely the case which amounts to Borel cohomology theories. It was later generalized by Lewis and May to the context of their coordinate-free equivariant spectra, and there was proved in complete generality, basically. In the context of orthogonal G spectra, where the setup is quite different from the Lewis-May setup, I have written up a proof in the Global Homotopy Theory book, and I will overlay the references for all these papers and books here. So this is a good point to end this third lecture. Next time I will go through a few examples of the double coset formula, both of the simpler one for finite groups or finite index inclusions, and also of an example of the general double coset formula here. In particular, the general formulation is quite abstract and not so easy to grasp, so I think it's a good idea to see an example. Now I would like to close for today, and thank you for your attention.